August 12, 2017. Bay of Naples, southern Italy. The Mediterranean is unusually calm. Divers descend slowly through cold green water. Beams of light flicker across broken stone blocks buried beneath the seafloor. Schools of silver fish drift through the ruins of an ancient Roman harbor. Everything is silent except for the hiss of oxygen regulators and the distant groan of waves above. One researcher brushes a hand across the submerged concrete wall. It should have collapsed centuries ago. Instead, it feels solid, unmoving, alive. The diver pauses and signals to the surface crew. Embedded within the ancient concrete are strange white mineral crystals. Formations modern engineers did not expect to find. Samples are carefully chipped away using underwater drills and sealed into containers for laboratory analysis. At first, the scientists believe they are studying a failed material. But over the coming months, they discover something astonishing. The concrete is not weakening in seawater. It is becoming stronger. One of history's greatest engineering mysteries returns from the depths. How did ancient Romans build harbors that survived 2,000 years? Storms, saltwater, earthquakes, and time itself. While many modern concrete structures crumble after only decades. To understand, you must travel back to the Roman Empire's peak. A civilization of roads, aqueducts, armies, and colossal architecture. But Rome's true power did not end at the shoreline. It began there. By the 1st century BCE, Roman trade routes spanned the Mediterranean. Massive grain ships traveled from Egypt, marble from Greece, olive oil from Hispania. The empire depended entirely on maritime infrastructure. Building harbors in the ancient world was extraordinarily difficult. Most civilizations relied on wooden docks or stone barriers. Salt crystallized inside cracks. Waves shattered foundations. Entire ports vanished after only a few generations. But Rome built differently. Along coastlines of Italy, North Africa, and the eastern Mediterranean, Roman engineers constructed enormous harbors directly into the sea. Some protected by curved breakwaters stretching hundreds of meters. Others used giant submerged concrete platforms beneath the waves. And against all logic, many still survive today. At places like Portus Julius, Caesarea Maritima, and Ostia Antica, archaeologists found Roman concrete intact after nearly 2,000 years. Modern engineers were stunned. Today's reinforced concrete deteriorates within 50 to 100 years. Saltwater corrodes steel reinforcement from the inside out. Yet Roman concrete contained no steel, no modern polymers, only stone, ash, lime, and volcanic material. The key ingredient came from volcanic land near Mount Vesuvius. Romans called it pozzolana, fine volcanic ash from Puteoli. Ancient architect Vitruvius described it in the 1st century BCE. Mixed with lime and rubble, the ash could harden underwater. Imagine standing on a storm-lashed coastline 2,000 years ago. Wooden cranes creak. Divers descend with baskets of wet concrete. Over time, rare minerals began growing within microscopic cracks. Seawater interacted with volcanic particles, creating interlocking crystals. Far beneath the Mediterranean waves, the ancient walls are still standing. The samples arrive in laboratories thousands of kilometers from the ancient coastlines where they were discovered. Inside sterile research facilities, fragments of Roman harbor concrete are sliced into microscopic layers thinner than human hair. Scientists lean over electron microscopes as glowing mineral structures appear across computer screens like alien landscapes. What they see should not exist. Modern concrete exposed to seawater usually suffers a slow death. Salt penetrates tiny cracks. Steel reinforcement rusts and expands. The structure fractures from within. Over decades, entire sections crumble beneath the relentless chemistry of the ocean. But Roman marine concrete behaves differently. The deeper researchers look, the more impossible it seems. Instead of signs of decay, they find evidence of growth. Tiny crystalline minerals have spread through the ancient material over centuries. reinforcing weak points like natural healing tissue inside bone. Cracks that should have widened appear partially sealed by new mineral formations. The ocean itself became part of the engineering process. And suddenly, the Roman harbors no longer look primitive. They look revolutionary. To understand how extraordinary this was, you must imagine the ancient Roman world at its height. During the reign of emperors like Augustus and Trajan, Rome controlled vast territories. Stretching from Britain to North Africa, the empire spanned 3 continents. Feeding the empire required enormous maritime logistics networks. Grain shipments from Egypt alone fed hundreds of thousands of people inside the city of Rome. Without durable ports, the empire could collapse. Roman engineers knew this. Harbors were not simply docks. They were lifelines. At massive port complexes like Portus near Rome, engineers created artificial basins protected by curved breakwaters. These structures absorbed wave energy before it could damage incoming ships. Some harbors included lighthouses, warehouses, drainage systems, and hydraulic concrete poured directly into open seawater. The scale was staggering. Ancient writers described construction barges carrying enormous wooden cranes capable of lowering stone blocks weighing several tons. Laborers worked waist-deep in seawater under the relentless Mediterranean sun. Supervisors measured angles using ropes, plumb lines, and simple sighting instruments. Everything depended on precision. Because underwater concrete is difficult even for modern engineers. Modern marine construction requires advanced pumps, chemical retardants, reinforced steel cages, and controlled curing. Yet Roman builders achieved similar results using materials gathered from volcanoes and lime kilns. The hidden truth lay in chemistry they did not fully understand, but mastered through experience. Roman concrete was created by mixing volcanic ash with lime and chunks of rock called aggregate. But unlike modern cement systems, the Romans often used seawater directly during marine construction. That detail changed everything. When seawater entered the mixture, it triggered slow chemical reactions between volcanic ash and lime. Over decades, even centuries, these reactions formed rare minerals inside the concrete matrix. One of the most important was aluminous tobermarite. This crystal structure is extremely resistant to fracture and strengthens surrounding material over time. In modern industrial settings, creating similar minerals usually requires high-temperature environments. Yet the Romans produced them naturally inside seawater-exposed harbor concrete. Not through advanced science, but through observation. Generations of Roman builders noticed that volcanic ash from the Bay of Naples created unusually durable structures. The material was so valued that ships transported pozzolanic ash across the Mediterranean. Cargo vessels arrive at crowded Roman ports carrying mountains of gray volcanic powder. Workers shovel the ash into storage pits while architects oversee massive harbor expansions. Blacksmiths hammer iron tools while waves slam against unfinished breakwaters under dark winter skies. One of the most famous examples stood at Caesarea Maritima, built under Herod the Great in the 1st century BCE. The harbor was one of the largest artificial ports in the ancient world. Roman engineers poured hydraulic concrete into enormous wooden forms underwater, creating foundations where none existed. For ancient sailors approaching the coast, the sight must have seemed impossible. Stone piers rising directly from the sea. Yet, after the fall of the Western Roman Empire, much of this knowledge slowly disappeared. Meanwhile, Roman harbor walls remain beneath Mediterranean waters, silent, unbroken, still interacting with the sea exactly as they were designed. For centuries, the ruins stood in plain sight. Broken Roman harbors lined the coasts of Italy, Greece, North Africa, and the Levant. Fishermen tied their boats beside ancient submerged piers. Waves crashed endlessly against concrete walls first poured during the Age of Emperors. People admired them, but few truly questioned them. Not until modern structures began failing. In the late 20th century, engineers across the world faced a growing crisis. Reinforced concrete deteriorated faster than expected in marine environments. Bridges cracked, seawalls weakened, Ports demanded expensive repairs after only a few decades of saltwater exposure. Entire industries formed around slowing corrosion. And yet the Roman structures remained. That contradiction disturbed researchers. If modern engineering possessed advanced chemistry and steel reinforcement, why were ancient harbor walls still outperforming contemporary designs? The question sparked intense debate among archaeologists and scientists. Some believed the answer was purely geological. Mediterranean waters were less destructive than open oceans, they argued. Perhaps Roman harbors simply survived because conditions were favorable. Others pointed out survivorship bias. Only the strongest examples remained. But the evidence refused to disappear. Roman marine concrete was not merely enduring passively. Mineral reactions inside continued evolving after nearly 2 millennia underwater. That was difficult to explain away. At University of Utah and laboratories in Italy, scientists studied ancient samples. Under powerful imaging systems, they observed networks of intergrown crystals, threading through the material like microscopic reinforcement fibers. Seawater dissolved portions of volcanic particles inside the concrete, releasing elements that slowly reorganized into new minerals over centuries. The process resembled geological transformation more than ordinary construction. Roman harbor concrete was behaving almost like artificial rock. That realization led to a radical theory. Modern concrete may actually prioritize the wrong goals. Today's industrial cement is optimized for speed and efficiency. Modern concrete hardens quickly, but becomes brittle over time. Roman concrete hardened far more slowly. But perhaps that slow transformation was precisely its strength. Ancient builders created a material designed to improve over generations. If true, modern civilization abandoned durability for convenience. Steel-reinforced seawalls require constant maintenance. Saltwater creeps invisibly through microscopic fractures. Entire budgets are dedicated to repair cycles before structures reach a century. Now imagine a Roman harbor.
No steel.
No electricity.
No industrial chemistry.
Yet sections still remain after earthquakes, invasions, and nearly 2,000 years of tides. The comparison feels almost impossible. Naturally, skepticism followed. Ancient concrete was not universally superior. Modern reinforced concrete allows enormous tensile strength impossible in Roman construction. Roman marine concrete excelled in specific conditions. It was not magic. Still, modern researchers struggled to reproduce the material exactly. The volcanic ash came from regions near Pozzuoli and Mount Vesuvius. As Rome fell, the engineering traditions slowly faded. By the medieval period, ancient Roman harbors became mysterious ruins. Today, underwater archaeologists still explore submerged Roman ports. The ancient world may have understood sustainability better than modern industrial society. Night falls over the Mediterranean. Waves roll through Roman breakwaters along Italy's coast. Columns damaged by earthquakes still rise like drowned monuments. Beneath sand and sediment, ancient harbor walls remain untouched, silent, enduring, waiting. For engineers, the greatest mystery has changed. The evidence is overwhelming. The mystery is why humanity allowed this knowledge to vanish. History tells of civilization climbing steadily upward. But Roman harbors challenge that comforting narrative. They reveal something deeply unsettling. Progress is not always permanent. Knowledge can vanish. Entire systems of engineering can collapse with their civilizations. The Western Roman Empire fragmented in the 5th century CE. Trade routes became unstable. Cities declined. Political authority fractured across Europe. State-sponsored construction projects nearly disappeared. The empire could no longer maintain its own infrastructure. Slowly, the secrets of Roman concrete faded into obscurity. Volcanic ash called pozzolana grew harder to obtain. Skilled builders disappeared generation by generation. Written texts survived only in fragments copied by monks. Even beside Roman ruins, people no longer understood them. Imagine a medieval traveler arriving at an ancient Roman port. Broken arches extend into the sea. Massive submerged blocks vanish beneath green water. Strange concrete walls still stand against the surf. To the traveler, it felt less like architecture, more like the work of giants. Over centuries, myths replaced engineering memory. Roman ruins were seen as relics of lost golden ages. Others became quarries for newer cities. Stones were reused in churches, fortresses, and roads. Yet the harbor foundations endured. The sea kept testing them, and still they survived. Today, researchers see lessons for sustainable engineering. Modern cement production releases enormous carbon emissions. Modern infrastructure demands constant repair and energy. Roman concrete used lower-temperature lime and volcanic materials. Scientists investigate whether similar techniques could last longer. In laboratories, experimental Roman-inspired concretes are tested. But recreating the ancient material remains difficult. Not only because of chemistry, but because society builds differently. Roman engineers thought in centuries. We think in decades. Ancient harbor projects were designed with rare patience. Roman concrete cured slowly, growing stronger over generations. It became stronger through continuous interaction with seawater. The ocean was not their enemy, it was their collaborator. That philosophical difference may matter as much as the recipe. Today, rising seas and violent storms threaten our coastlines. Researchers study Roman harbors not from curiosity, but necessity. The ancient ruins have become strangely modern again. Divers descend with digital scanners and underwater drones. Sediment cores are extracted from harbors abandoned 2,000 years ago. Chemists analyze volcanic crystals mixed by forgotten Roman laborers. The past is being excavated not only for history, but for survival.